everybody. Welcome to this event, and welcome also to our moderator Antonio Stone, Professor Piercarlo Muscarelli, and as well Claudio Chesi from Milanite, professor from Università Bicocca di Milano, and Enrico Di Martino from Asso Resorts. Okay, I am Fabrizio Rollo, the new Italian section chairman, and it's my first event actually, and I'm very happy to be here and to introduce this very actual and an interesting topic about raw critical materials and next generation batteries. An event that is particularly actual in this historical moment, which is an unprecedented historical moment where so many things are mixing up at the same time. So some define this period as the perfect storm, where we have so many things mixing up. But if we take just a portion of that, and if we focus only on the technologies, what is happening is that there is a mix of many things happening. The development of new decarbonization technologies that are required to set and to target the very ambitious goals of net zero in 2050. We have the continuous ramp up of renewable energies and technologies related, and all the electrification topic connected. We have the need to digitalize all the systems to make them more efficient, and it's becoming a must to survive also in the current market, and so many other advanced technologies. So what do all these technologies have in common is the need for raw critical materials. And this is the reason why a race has already been started in order to secure the access to these very limited resources that, by the way, are not spread in a homogeneous way all around the world. And if we think about it, what happens and the criticalities related to these things are not that different to the current situation on oil, gas, energy supply, and commodities. So therefore, the need to diversify the supply as much as possible in order to be as less exposed to potential market upset. So this is the reason why, for example, in Europe, very recently, the European Commission has done a legislative proposal, which is called the European Critical Raw Material Act, where they try to boost the supply in order to limit and to reduce the dependency from a country like China, where more than 90% of rare earths are concentrated, and more than 60% of lithium is processed. And this is also the reason why also in Italy the topic is becoming always more and more sensitive. And a few weeks ago, both the Ministers of Energy Transition and Development Economy, Ministero della Transizione Ecologica e Ministero dello Sviluppo Economico, has released an interministerial decree with the purpose of formalize a technical table already existing, where Asso Resorts is present, and they will tell you more about it, with the purpose again to put in connection this time research center, institutions, associations, again with the final goal to make proposals which are not only technical proposals but also are normative and business model proposals. Therefore, I'll stop it here. I pass the microphone to our moderator Antonio Stone. Thanks again for coming over tonight, and enjoy the session.
Can you hear hear me also without mic? I prefer it. Okay, thank you, Fabrizio. You say that this is an interesting topic. Yes, it's true, but I have to say that it's also a very complex topic from a technical, from a technological point of view. I'm not a technical guy. I'm not a technological guy. I'm a sustainability practitioner, or ESG today. We say ESG practitioner. Why a sustainability practitioner, sustainability expert is involved in a topic like this? For the complexity. And the complexity, as you say, starts with the fact that the localization of rare earth material are only in some geographies. I have to share with you also an important statement. Nevertheless, the name rare earth material, they are not so rare. So it's quite available in nature. The problem is that to extract, so the availability of the material requires a lot of processes that are very polluting processes. That's the problem, that's the main link with sustainability. I can share just one information, just one data. For some rare earth material, the production of 1 ton means 2,000 tons of toxic waste. And if we, can we go? Okay. And so this topic, this is the reason why this topic today is very high in the agenda of sustainability professionals, but also on the sustainability department of the companies. These are 2 images. You probably, based on the architecture, you can recognize also the location. 2 images of the so-called cancer villages. This is the results of this type of processing for extracting the material. These are death zone with impact to people working there, to collectivity living there, and also to biodiversity. So that's the problem. This is the connection with sustainability. On a general scale, what is the secondary problem after that? Is the fact that if you see the localization, and our speakers will show us where these rare earth material elements are located, we are referring to countries that are not always very strong in environmental and social regulation. And this is the second problem. The second problem is that today, even if it's possible to locate and to access to these elements in other parts of the world, the cost for producing and at the same time to comply with the law is very high. Also here, just one data, one information for some of these elements, the cost of producing in Western countries, according to Western regulation, is 20 to 25 times higher than producing in that area, in this area. So this is the connection with sustainability. And is a top on the agenda. It's we are facing a bit of paradox because rare earth are important elements for the energy transition, lithium and other that we will see. Are important element for producing better product, sustainable product, but unfortunately the sourcing is affected by this type of problem. So it's a bit of paradox. For doing something good, we risk to work with supply chain that are very, very critical from a sustainability point of view. And as Fabrizio said, there is now a very important action by the authorities, by regulators. This is a news from 3 weeks ago, and Madame Ursula von der Leyen is talking about fight for rare earth resources. And we are having, as you can see, some problem with the access to gas, to energy. This is at the same level, if not even more. China, in particular, decided in late 80s to identify rare earth extraction as a strategic sector, and they have now accumulated an advantage which with this action we have to cover. Okay, very short intro. Now I leave the stage to Claudio Chesi. He's a technical guy for me. He worked in R&D applied to rare earth material, so he will introduce us to this theme. He's going to show which are the long list of rare earth material and a lot of additional interesting information.
Thank you very much. So can you hear me with only the voice, or may I use the microphone? Are you fine with my voice? Yes. Okay. So good evening, everyone. I'm Claudio Chesi. I'm a geologist. I work in ENI since have been working in ENI since 2018. And today I'm going to provide you an overview about the much discussed topic of critical elements or critical raw materials, with a special focus on the geological aspects of lithium and rare earth elements. Okay, so first of all, what are these critical elements? The first definition dates to the early 2000s, when some main world institutions, such as the European Union or USGS, started to acknowledge that some elements or materials are essential will be essential for the development of clean energy technologies, and so to deliver on the climate ambition for the next decades. As you can see from this very colorful image on the left, the type of elements vary by technology. So, for example, lithium, nickel, cobalt, manganese, and graphite are crucial for battery performance, longevity, and energy density. Rare earths are essential for permanent magnets, which are vital for wind turbines and electrical vehicles, and so on. As you can see from the periodic table, the list of elements is very long, but of course, for the sake of brevity of time, we will see just some examples of these critical elements. Okay, so we've seen that these elements are critical primarily because of their essential contribution to the energy transition. But this is not the only reason. The shift to a clean energy system has begun to drive a huge increase in the requirements for the critical minerals, that are the mineral resources from which many of these critical elements, if not every critical element, are recovered. Of course, they were recovered in large amounts even in the past, but their world demand has skyrocketed in recent years due to 3 international treaties, all of which pushing towards more renewable sources and clean storage technologies. And this is expected, is forecasted to rise more and more in the future years. But this raises some questions and doubts about the availability of these critical elements and the reliability of supply of these elements. Also because the extraction and production of many of these energy transition minerals is even more concentrating than that of oil and gas. As you can see, for example, from this graph on the bottom left, China, for example, has a strong presence in the production of rare earth elements, but also in the processing of many critical minerals or critical elements. Okay, so we've seen that the second reason for which these elements are called critical or precious is the vulnerability of their supply chain, mostly because because of the concentration of the extraction, the production, and processing operations in a very small number of countries around the world. Sometimes also characterized, as Antonio was saying, by a very high geopolitical instability, and this is also a big problem In some cases, for example, a single country can be responsible for half of the world's production of a single element, and this, of course, is an important problem. The common graph then adds one more information. It shows that in most cases the problem of geographical concentration of production is unlikely to change in the near term. So, for example, unless significant changes occur, China will be probably the lead producer of rare earth elements even in 2025. Okay, so today, of course, we don't have enough time to see each critical element of critical mineral, so I decided to show you the main aspects about two of them, lithium and rare earth elements. Rare earths because they are considered by many as the most critical group of elements in the long list that you saw before. And we will see in the next slides why I chosen also lithium. So, starting from rare earth elements, the rare earth elements group include a group of 17 elements that are not that rare in nature, but rarely occur as economic mineral deposits. So you can easily understand that the problem of geographical concentration, in this case for rare earth elements, is even more important because they are rare as mineral deposits. China, as we will see in the next slides, hosts, for example, the biggest mineral deposits of rare earth elements, and so is by far the lead producer of supplier of rare earth elements in the world. So, but where do rare earth elements occur in nature? The list of minerals, including rare earths within their chemical composition, is quite large, it's quite long, but only 3 of them have concentration high enough to sustain economic development, economic production. They are pesnazite, a fluorocarbonate, and monazite and xenotime, the other 2 phosphates. These minerals can occur in 4 main geological settings. The first setting is characterized by the so-called carbonatites that are a peculiar type of magmatic rock that is characterized by more than 50% of primary carbonate minerals and less than 20% of silica. They are commonly found in association with another type of magmatic rocks called alkaline intrusive rocks that are as well deficient in silica with respect to the alkali oxides. Then we can have even higher concentration of rare earth elements if these types of rocks are subject to a tropical alteration, so the formation of the so-called laterites, leading to the so-called supergene enrichment. It is a mining term indicating this process. Then there is one last type of deposit characterized by the erosion of these minerals enriched in rare earth elements and their deposition within sedimentary succession called placers. So we have understood that these rare earth deposits, mineral deposits, are rare, but where they occur in the world. As you can see from this map, this is the location of the main rare earth deposits in the world. Probably if you compare this image with the one that we will see in the next slides about lithium, you can easily notice that there are few. There is a few deposits of rare earth elements in the world. Just one more information. If you look at the table, I just want to draw your attention on the striking difference between the amount of reserves at Bayan Oro, that is the first, the top producer of rare earth elements, and the second one, that is the Araxá deposit in Brazil. In the next slide, we will see a brief detail on the Bayan Oro deposit. These Chinese mineral deposits, it's really something unique as for rare earth elements. It's also the second largest niobium deposit in the world, and data shows that it hosts 42% of the world's rare earth reserve base and accounts for 86% of the total world production of rare earth elements. The ore deposits consist of massive dolomites enriched in these minerals, pesnazite and monazite, as we've seen in the previous slides, accompanied with a various kind of rare earth and niobium minerals. The origin of this deposit geologically is something that is still debated, but probably is related to a carbonatitic magmatic event occurred at about 1,400 million years ago, probably related to the breakup of a supercontinent, so something probably very, very large. So once we have extracted the minerals from the hard rock, these minerals must undergo a series of processing operations in order to upgrade their concentration up to about 60% to be processed further to obtain the product for the trading, let's say. So of course, methodologies can vary according to the type of mineral, the type that is present in the ore deposit. For example, the Mountain Pass mine in California represents a standard for the processing of the mineral bestnasite, while monazite and cenotyme, two phosphates, must undergo a series of different processing operations to be processed. Okay. So now let's move to the second element, that is lithium. Lithium is why it's critical. Lithium is critical. It's one of the most discussed elements also, even though it's really relatively abundant on the Earth, and it's not too critical at present day. But it has unique physical and chemical properties that make it essential in many applications for clean technologies. Moreover, lithium has a big problem of geographical concentration, both for extraction, that is mostly concentrated in Australia and in South America, and for processing, that is mostly concentrated in China. So you can these problems probably are expected also to become more and more important in future years, exactly because of the increasing demand of the element. Okay. So same question, similarly to rare earth elements. Where can we find lithium in rocks, in minerals? Lithium is a highly reactive element, so it's present in a very large number of minerals, more than 100 known. But only 3 of them are the minerals used for economic processing. The first one is the pyroxene spodumene. The second one is the clay mineral pectorite, and then there is the silicate jadarite. Spodumene is the most abundant lithium-bearing mineral in the economic deposits of lithium, while pectorite and jadarite are present in volcanic-related environments such as volcanic calderas, and are minerals that are expected to become more and more important in the future years. Jadarite is also known for a funny aspect because its chemical composition is very, very similar to the Superman's kryptonite. Where can we find these minerals in rocks, in geological environments? Basically in 3 main geological environments. The first one consists of continental saline lakes characterized by very high evaporation rates. They are mostly located in South America and accounts for about 60% of the total reserve base of lithium in the world. So they are very, very important, probably will be more and more important in the future years. The second setting is characterized by a peculiar type of magmatic rocks called ferralkaline intrusive rocks and paraluminous pegmatites, typically associated with the mineral spodumene. Pegmatites are a peculiar type of rocks that form in the late stage of magmatic crystallization, and is often characterized by very large crystals and very strange minerals enriched in the most incompatible elements contained in these magmatic fluids in the magma. Then the last setting is, as we've seen before, is the volcanic environment, preferentially the one characterized by very enriched in silica that can host accumulations of pectorite or jadarite. As for rare earth, here we can have a global view of the distribution of the main lithium sources. Australia is the top producer of lithium from pegmatites, so from the mineral spodumene, while lithium from brines is mostly extracted and produced in South America, in the salars of South America. On the left, you can see a zoom of this region of South America, in which you can clearly see the high number of these continental saline lakes, also called salars, of very different size along the Andes. They are collectively known as the so-called lithium triangle, that consists of Chile, Bolivia, and Argentina, that altogether accounts for 60% of the total world's reserve base of lithium. Just one more information, in the table you can see a list of the top 4 world-class deposits of lithium, as for mining, and just want to note that the first 2 are related to the volcanic environment, so clay minerals, that are expected to become more and more important in the future years. Okay, these are just 2 examples of world-class lithium deposits in rocks, so in minerals. The first one is in Mexico and it's called Sonora, and it's the typical clay-hosted ore deposits accumulated within a volcanic environment, and is currently under evaluation of resources and reserves. The second one is the Greenbushes mine in Western Australia, and it's the world's largest operating mine for lithium minerals. It's characterized by zone pegmatite, and in this pegmatite, for example, the mineral spodumene can account for about 50% of the total pegmatite deposit. So we've seen that lithium can be extracted from brines and from minerals, the minerals from spodumene and clay minerals and related. So from brines, the main compounds are lithium carbonate and lithium oxide hydroxide, that are compounds essential for batteries manufacturing and the primary forms of lithium traded worldwide. A concentration of lithium in brines is challenging because, for example, magnesium has a negative effect on this process of concentration. As for mining, lithium is extracted employing mainly an open pit mining that probably will become more and more precise and more cheaper in the future. And as you can see, the main product also of the processing of lithium minerals is the lithium carbonate. Okay, so just moving towards the conclusion of this presentation, as you probably remember from the periodic table, the list of critical elements is way longer than just lithium and rare earth elements. These are just 3 more examples, but I will not enter into the detail of these 3 elements. For example, cobalt is a commonly byproduct of copper and nickel ores, and an interesting fact that is important resources of this element are present on the sea bottom, but this will probably be a challenge for the future years. Magnesium is very abundant in the Earth's crust, but magnesite reserves are located mainly in Russia, China, and Korea, so it can be a geopolitical problem. And also remember that it's critical also to the production of lithium in a negative way. Then strontium is very important for the development of permanent magnets, and it's generally hosted within sedimentary successions. So just to conclude this presentation, we've seen, these are just the main take-home messages. So we've seen what are critical elements and why they are called like this. They are 42, according to the most updated lists. They are characterized by vulnerable supply chains, and they are essential for the development of clean energy technologies. So probably, let's conclude just by saying that the world of energy industry is going to face some major challenge in the recovery of natural resources. And so probably the best way to address this situation, to cope with this situation, is the construct of a robust groundwork focused on critical minerals that are the focus of this presentation. And probably they are rare, but probably their rareness is associated also with the fact that they were unexplored in the past in the existing mines, because they were not considered critical. So probably this will be a very important change in the mining exploration in the future years. And scientific research is expected to play a major role in this sense by helping us to giving us the tools to detect and study these critical minerals. So thank you all for your attention, and
if you can stay here, we have a short Q&A section at the end of each presentation. So if anyone has questions, comments. for the moment. Maybe I start with a with a question. You said that today there are 42 elements, rare earth, lithium, and other. You already say something, but do you see these as a closed list, or do you think there will be some updates in the future based on the development of the technologies, and what are your thoughts? Which direction we are going?
Thank you very much for the question. Very interesting. So the list is continuously updating. For example, European Union has planned to update the list every 3 years. So, for example, the new Union Europeans list will be delivered in 2023. So in just a few months. So we'll see if they will confirm this the list. But I can say that the change of the list is mostly related to the way probably in which the demand of these elements is going to change in the future years. So you've seen at the beginning these graphs, these rising curves, and so related to the technologies, as you were saying. So seeing what element becomes really critical in this moment, and also in forecasts for the future years.
Thank you.
I have a question. I do understand that the economicality of the process of production is an important part for considering whether the material is critical or not, right? So, and I see some analogs with the oil and gas and between resource and reserve. So something that is today critical might not be tomorrow because of technological advance. So the question is, if the economical process might drive the criticality, is the criticality depending also on the specific country that you are looking at and production process, or more or less the drivers are the same?
No, it's certainly related also to the countries, because, for example, I can make also the example, because we've seen the slides of lithium. Because, for example, lithium now, for example, is produced from minerals in Australia that has the biggest mines. But many of these mines, for example, are being acquired by Chinese companies. So the problem is also that some country probably in future will expand their influence also on other countries, and this is certainly a problem because. As we've seen before, there are environmental problems in the sense of the processing operations, but also just the presence of one single country on too much operations of extraction of the element around the world. So this is certainly a big problem. Also because, for example, for lithium, the processing is also currently in the hands of China. So if China expands their influence also on the production operations, it can be more dramatic for lithium. So lithium can become more and more critical. This is just an example of lithium, but it can be applied also to other elements. For example, rare earth elements that are the most critical group of elements.
It's to me the same process that we had with another set of elements which are conflict minerals. So conflict minerals and very in focus during this type of element. We have a very strong relation in US and Europe, and the situation you described is exactly the same. So conflict minerals came from conflict zone, typically DRC, Central Africa, but now the purchase is only in one direction. So probably there will be some similarities during the future. Okay, thank you. But we are going to have some additional room for questions with Claudio at the end. Now I introduce Piercarlo Mustarelli from Bicocca University, and he is going to talk about a very important element for the energy transition, lithium. And also this, I hope you can enjoy a very technical insight about this work.
I hope you will enjoy. Good afternoon, evening, everybody. I will discuss of lithium batteries with emphasis on three aspects: performance, safety, and sustainability. The next one. I don't know what your background is, so let me start from the very beginning. That is the scheme of the battery all of you have in your pocket. It's the famous Sony model of 1991, where you have a anode compartment here made of graphite, a cathode compartment here which is made of an oxide, a lithium cobalt oxide, and an electrolyte which is a liquid electrolyte made of an organic solution with lithium salt. Okay, during the discharge of the battery, the lithium ions go from the anode to the cathode, and during the charge, the opposite behavior is taking place. These batteries explode, you know. They really explode. Why? Because there are two main issues: the composition of the liquid electrolyte and the reaction with the electrodes. Okay, the thermal process which make the battery to explode is called thermal runaway. It can be simulated by instruments. For example, you can see here this red curve. This is a battery which is artificially heated, and at a given point there is a spontaneous reaction increasing the temperature up to 250 degrees centigrade. Here the battery explodes. You can modify this by changing the electrolyte, for example, by using ionic liquids or more stable liquids. You can follow other behaviors, but at the end you will always have explosion. Okay. So the problem is the main safety problem is to solve the issue of the liquid electrolyte. But let's start to discuss about performance. The next one. This is a very famous picture which explains very clearly what is the roadmap to be used in increasing performance. First of all, the energy of a battery is proportional to capacity and potential. Here you find anode materials on the bottom, cathode materials on the top. So, in order to increase the energy, you should increase the potential difference between the anode and the cathode, or the specific capacity on the x-axis. One touch, please. At present, we are working there, graphite anode, and some spinel or other oxide cathode. Okay, these are the actual elements which allow us to make with the car 1 kilometer with 1 kilogram of batteries. Consider this figure. So the issue is to move in this direction. Another touch, and we should go there. Okay, new cathode materials, new lithium metal as the anode. This way we can double the energy density of the battery. Okay. The next one. This means to move from the so-called 3A generation battery, which is still now on the market, made of a NMC, nickel, cobalt, manganese cathode material with different amounts of nickel, cobalt, and manganese, and an anode made by graphite with a small amount of silicon. These are on the market. But in order to improve the energy density from this point, this is the physical limit, gravimetric energy density against volumetric energy density, okay? Now we are here. This is the limit of the lithium batteries with the liquid electrolyte. In order to go here, we need to substitute the anode with lithium, but this will require to move from liquid electrolyte to the solid one. Okay? Solid electrolyte, which can be made of polymers or composite materials, polymer ceramic materials. Just a brief story. In 2010, I was in Rome at a conference, and during the banquet, I discussed it with people from Toyota, and they told me, it's a matter of few months. We will exit on the market with our solid electrolyte. Not yet. Okay, just to give you an idea. But this means to move from year to year. This means to double the gravimetric energy density, passing from 2,000 to 250 to almost 500 watt-hour per kilogram. This means to make 800 kilometers with your Tesla, okay? Not 400, 800. Well, let's move on. The substitution of liquid electrolyte with the solid one has a very strong impact on the safety problem, because with the liquid electrolyte, you have protrusion of lithium during the charge and discharge processes, and this protrusion will, called dendrites, will cause short circuits. Then in turn will increase the temperature of the battery. You probably see that your phone becomes hotter and hotter. This is due to some short circuit in your system. So, but by substituting the liquid electrolyte with the solid one can solve this problem. And this is one of the main research topics to improve safety, both performance and safety. There is another important point, the next one please. Okay, this is the passage from liquid electrolyte to the solid one, which can be obtained by changing the lithium salts, by using new solvents, and finally by using polymers. Okay, but the next one. Another important issue in order to improve the safety of your battery is the use of the so-called self-healing materials. Self-healing materials are materials that are able to heal your battery during operation. There are two main categories: extrinsic and intrinsic one. With the intrinsic self-healing materials, the situation is ideal in a sense that your battery is breaking. Okay, inside the battery there will be some components which will repair automatically your system. For example, polymers which are able to make crosslinks. In the extrinsic way, in contrast, you need a sensing system. For example, you need to sense a variation of pH or temperature or pressure inside the battery, and then by means of some actuators, for example ultrasounds, you can tell to the battery, okay, now please repair yourself. European Union is financing many projects in the frame of Horizon Europe on both these topics. The dendrites elimination, moving to solid electrolytes, and moving to self-healing materials. The next one. But let's now move to the problem of sustainability. Well, this is the growth rate expected from now to 2030, a 14 increase in global battery demand. This scale is in gigawatt hours, and you can see that the main increase is related to automotive. But also from the point of view of the regional division, you see that China will operate very, very strong on this market, okay? So let's consider this terrible increase. The next one. So we will focus our attention on the automotive market, which is the most important, the most demanding, the most critical, okay? Well, this is the pack, the battery pack. Just to give you an idea, if you consider the 18650 cell, which is a cylindrical cell of this dimension, a Tesla 990 has 7.5 thousand cells of this in the pack, here inside. The pack is divided into modules, and the module will contain a cell. We have three main kinds of cells: cylindrical, prismatic, and pouched. The most common now are cylindrical, okay? Let's consider this pyramid, okay? The next one. And let's consider what is the expected increase of raw materials needed to follow the requirement, to satisfy the requirements of the automotive market. This is the increase of the main components of the battery, not only lithium, but also graphite. The anode is made, as I told you, the present anode is made chiefly of graphite. Consider 100% of graphite in China, okay? Lithium, nickel, cobalt, manganese. The lithium demand is increasing this way, but all the materials are increasing, and we also will have a strong increase of the kilotons of lithium-ion batteries to go to recycling, and this is an incredible problem. I cannot enter the details too much, but please. This is the lithium demand in gigawatt hour. I don't know about the mining capacity, price, or I don't know. It is not my work. But let me consider this point. Inside the battery, the main part of the cost is given by the cathode, and inside the cathode, the main part of the cost is given by nickel, and then by manganese and cobalt. Okay, these materials will become critical. So some of them are already critical, cobalt and nickel, but also manganese will become critical. So this is a very, very important problem from the point of view of the sustainability, and we need to discuss about this. The next one. Claudio showed the situation of lithium. I will show the situation of cobalt very, very quickly. You could think, okay, cobalt is quite well distributed. One touch, please. 70% in Zaire. Zaire means China. Okay. The next one. So we need to change our mind and to move towards a circular economy approach. We need to take natural resources to make batteries, to finish to use the batteries for the primary use, and then not to go directly to the end of life. But we need to refurbish the system to go, if needed. For example, by taking the battery from the car and put on the photovoltaic plant to store. We will have a second life. After that, we need to recycle. And only at the end, possibly a very small part of the overall production should go to the disposal. This is very important. The next one. This will require the so-called battery passport, because people, for example, to refurbish or to recycle, must to know which chemistry is inside the battery. Lithium cobalt rather than lithium iron phosphate, rather than MNC, because different materials will require different treatments. Okay, this is critical. The European Community is moving in this to this direction. Okay, the next one. From the point of view of the value chain, we take the resources, we produce batteries, packaging, use service, collection. Every passenger will need energy, and in principle will produce waste. So we need, from this point, to follow several paths. Simple reuse, as I told you, or repair, or even remanufacturing for say, upgrade or even downgrade. And we also need to close the loop for recycling. How can we recycle batteries? The next one. I am at the end. Okay. From the end of life battery, after the second life, we need to make some mechanical treatments to open the battery and so on, to separate the compartments, and we need to obtain the so-called black mass. In this sense, the battery passport is important, because I must know what kind of black mass I have. So we can follow two main different routes: or direct recycling, chiefly the cathode, or by means of pyrometallurgy or hydrometallurgy routes to separate the different elements in order to obtain new raw materials, new raw compounds. The next one. From the point of view of Europe, the ecosystem is very complex. Now, the main subject, the main structure in this sense is the battery partnership, which has a private part and a public part. This is the structure which will prepare the new goals for Horizon Europe in the field of battery. Let's move to the next one. From the point of view of the research, moving from TRL1, which means the idea, to TRL9, which means the product is on the market, we have three different structures working in Europe. Battery 2030, a mixed industry university association working on low TRL. Batteries Europe, which was set up in 2019, and then IBA 250, which is the Association of Industries, moving to higher TRL. What finally at the Italian level, the last one, okay, this is the ecosystem concerning the factories which are active or which are thought to be active from now to 2030. You see, in Italy we have FAM in Caserta, and we will have also internally the gigafactory from Stellantis. We also, but in Italy we have two. In Italy, the next one. We have two initiatives. One is this diesel NSTM, Gruppo Italiano per Sistemi di Accumulo Elettrochimico, that joins practically all people working on the electrochemical batteries. And in Lombardy we have this new lab jointly with Bicocca Pavia and Politecnico di Milano and CNR in the frame of a project called EcoSys. This is intended to work on reuse and recycling. Okay. It's all for me. I hope to be in time. I'm not sure.
Yeah.
Take home message. Lithium batteries we don't believe are sodium batteries. No. For 20 years lithium batteries. It is necessary to reduce the dependence from China. It is necessary to increase safety and sustainability. There is, following Feynman, a very plenty of room at the bottom. It is possible to make many initiatives concerning reuse, refurbishing, and recycling.
Domande? Ne pongo una. Okay, we mentioned many times today the dependence from China and for all the elements and materials we mentioned. What is your opinion about the actual possibility for Europe to break the Chinese monopoly?
Only, okay, we have two routes. The first route is to develop very powerful recycling methods. And the second one is to improve technology, because Chinese are very able to set up low-level technologies. But for example, if we move to batteries with the sensing and self-healing features, it will be much more difficult for them to follow us.
Okay. That's a very good point. Any other question? No? So we can move to last, not least, speaker, Enrico Di Martino, the presentation of Asso Risorse, and Enrico will tell you something extremely interesting. We will move from now the description on what Italy is actually doing today for managing several issues that we discussed today.
Thank you very much. So good evening, nice to meet you all. My name is Enrico Di Martino. I'm here on behalf of Asso Risorse, and I'm working in a consulting as head of research and innovation for the Energy and Mobility business unit, where I lead a team of around 20 people, scientists and engineers, and with my team we manage around 75 European funded research projects. So today I will present Asso Risorse. I will talk about the Italian institutional table on critical raw material. I will explain the battery role for the road to net zero, and I will show something similar that the professor has shown before about the expected demand on batteries. I will present the BAT4EU partnership, the European vision, the 6 focus area for research and innovation about batteries, and I will very shortly introduce one research project that we are following as RINA for long-lasting batteries. And then I will begin with the presentation. Next slide, please. So, as I said, I'm here on behalf of Asso Risorse and on behalf of our executive vice president in RINA, that is Leonardo Brunori, that is also the vice president of the Asso Risorse service sector. So Asso Risorse is the Confindustria Association derived from Asso Mineraria, the Italian mining association. They have around 100 companies committed to enhance the natural resource and intellectual skill through technological innovation and circular economy that aim to decarbonize industrial processes and achieve environmental, economic and social sustainability. So Asso Risorse companies provide both raw materials and develop highly specialized technology that are recognized worldwide for their excellence and operational capacity. So, as we have already said, critical raw materials are the key to achieving zero emission targets in the coming decades, and their demand will increase as the ecological transition takes place, while their availability may be insufficient with the risk of delaying the ecological transition. So the European Commission is committed to this issue, pushing member countries to implement a strategy aimed at ensuring a certain degree of independence of supply of these minerals. Next, please. Okay, so Italy has set an institutional table about raw material, where this table is participated by a lot of association institutions such as ISTAT, Enea, MISE, MITE, ISPRA, CNR, Asso Risorse, ITEC, and Confindustria. And the spirit of this table is to create an Italian system dedicated to enhance planning in terms of sustainability, supplies, and circularity of raw material. Next, please. So, the objective of this table is to define a national strategy to cover the potential lack of critical raw material through the identification of real availability in our subsoil of raw material, the identification of better performing technology for making attractive all deposits considered no longer economically viable, and also exploiting urban mining. Next, please. So, the new target for sure is to reach the net zero by 2050. Next, please. And to do that, we have to abate the most greenhouse gases contributors, which are construction, transport, and energy production. That together contributes to the 75% of greenhouse gases production. Then the transport and energy production are very related to batteries. So the transition from traditional transport and energy production to clean transport and energy production is very much related to batteries. Next, please. Okay, so the transport needs to be electrified. So the batteries plays a fundamental role, but also renewables needs to be integrated with storage system in order to take out the most from the renewable installation. Next, please. Okay, next, please. So, as we've already seen, the demand for batteries is steadily growing on different markets. And of course, also the raw material related to the battery production, such as lithium, cobalt, is expecting to increase, especially from the rise of e-mobility and storage for intermittent power generation that is expected in the future. Next, please. Okay, so from a European point of view, it has been established a partnership that is participated by private and the European Commission body. And the vision of Bat4EU is to establish the world's best innovation ecosystem in Europe by 2030 to boost a competitive, sustainable and circular European battery value chain and to drive the transformation towards a carbon neutral society. So next please. So the European ambition is to develop competitiveness, sustainability, industrial upscaling and market uptake. So they want to build a competitive battery solution. They want to build batteries with the lowest possible environmental footprint. They want to build an industrial plant able to produce several tens of gigawatt hour of battery each year. And they also want to integrate the batteries in the best way they can into the various functional systems. Next, please. So, the Bat4EU partnership has established 6 areas for research and innovation that are shown here. So we have 3 vertical areas, 2 cross-cutting areas, and 1 area that is about coordination. Next, please. The first area is about raw material and recycling. So the research here is focused on the processing of battery-grade primary and secondary raw materials, and also on the end-of-life management that includes collecting, sorting, dismantling, and recycling of batteries. Next, please. The second area is about advanced materials and manufacturing. The research and innovation is ongoing in advanced materials in order to allow better performing batteries, and also to change the material that is used to produce batteries. This research area is also focused on cell design and manufacturing of battery cells. Next, please. Then the third area is based on battery system for transport and mobile application, where they want to develop sustainable and affordable battery for clean mobility. And also they want to reduce the cost of battery system design, manufacturing, operation, testing, and end of life. And the other area within this research area is the battery system for stationary storage application, including second life application of EV battery. As the professor was saying before, it's possible to reuse the battery that are applied for electric vehicles for storage purposes. Next, please. And then there are the area 4, 5, and 6 that are about safety. So safety, of course, is a paramount to ensure the confidence and widespread adoption of e-mobility and electric energy storage in our society. And the solid-state battery will, of course, reduce the hazard of organic electrolyte. The fifth area is about sustainability. So the battery have to be designed for circularity. So the industrial process should ensure the closed loop and ensure the correct industrial synergies. The funding on the area of sustainability will also allow to develop tools for battery traceability, risk assessment, and also for tools for life cycle assessment and life cycle cost assessment. Last but not least, we have the coordination area that aims to coordinate the large-scale initiative for future battery technologies, and also to coordinate the platform to effectively develop, consolidate, and communicate a strategic research approach for all the stakeholders for the entire European battery value chain. Next, please. So, this is the project that we are following as RINA. So, LoRaBat is the name of the project and is the acronym for long-lasting battery. So, in this project, we are 17 partners, and the scope of the project is to develop through the entire value chain a rechargeable nickel-zinc battery with possibility to reach 4,000 cycle of that at the 100% depth of discharge. The aim of this kind of battery is to be environmentally friendly, since they are using abundant raw materials and non-toxic elements. This project is within the Bat4EU partnership and has been financed within the Horizon Europe program. Next, please. So the scope of this project is to improve the cell performance and cost, upscale the cell capacity to 100 ampere-hour, the construction of battery packs from 2.5 to 10 kilowatt hours with the battery management system sensors. We will, with this project, demonstrate the use of these batteries on 5 use cases in utility grids and industrial sites. We will also assess norm standards and grid compliance. We will perform environmental activities such as studies on recycling, LCA and LCCA, and we'll also take care of the exploitation of this research, developing business plan and market studies. Next, please. So this is how the partners of the project are distributed along the entire value chain of this project. So, as RINA, we are doing the exploitation part and the communication distribution. Next one, please. So, to conclude the presentation, of course, we have to provide the necessary. Europe and funding bodies have to provide the necessary funding for the next generation battery, and it's crucial to build an independent, competitive and sustainable European battery value chain. And also the 6 key areas that I presented provide a guidance on where key investments should be focused at least up to 2030 on research and innovation. And the more investment in development of advanced material will help to ensure the cost effectiveness of batteries, their sustainability, and increasing the safety of the battery technology that will help to increase the trust and demand of European batteries.
Okay. Thank you. Also here, any question? Otherwise, okay, I start. You mentioned the 6 focus area of the RNI project, and I saw that they span from very different topics, action type of initiatives. Which is for you the most important? How do you see the focus for achieving short-term results?
Yeah, I think that the most important research area is the first one that deals with recycling. Because first of all, we need to develop technology to recycle the batteries we have now on the market, and that will see their end of life in the future.
Thank you. Thank you. But recycling is, I think it's a quite interesting topic, also in the deployment of circularity. And we don't have to underestimate the impact of digital tools for circularity. Carlo mentioned the battery passport, and the deployment in Europe is more in the direction of a digital product passport. So this is the enabler for achieving the result. Okay. Thank you very much.
Thank you.
More question? Other question? I have to ask for the logistics now.
Yeah, we can start the
Okay. We are here for this. Okay.